Good morning, and welcome again to NYU from the campus of New York University. I'm Ted Rappaport, and welcome to the 6th seminar series in our exciting seminar, Circuits, Terahertz, and Beyond. On behalf of the NYU Wireless industrial affiliates that sponsor our work at NYU Wireless, and who are also involved in our research and recruiting and student activities, it's my pleasure to welcome you to a very exciting seminar today.
To come here. This is really great. It's been a fantastic visit already, and I'm looking forward to the rest of it. I'm here to talk to you today about my group's contributions and experiences in thinking about terahertz wireless. And this is something that as Ted said, I came to by way of optics. So I think I looked at the list of people who have participated in this great seminar series over the course of this semester, and most of them started at low frequencies and worked their way up, and I've come the other way. So they all consider themselves high-frequency people, and I consider myself a low-frequency person, but we're talking about the same frequencies. So it's really nice that the field is finally coming to a place where those two communities are now beginning to shake hands, right? As Ted was saying at breakfast this morning or at dinner last night, I don't remember. You know, one group started in California and started moving east, and the other group started on the East Coast and started moving west, and we're meeting in Utah at the Golden Spike and shaking hands, right? So this is fantastic. So what I'm going to tell you about are just a few ideas in devices for manipulating terahertz radiation and some measurements we've been making on trying to characterize terahertz channels. And a lot of this, sort of the overriding theme here is the photonics approach, the idea that we're thinking about these systems in a photonics sort of way, right? For me, terahertz is not a broadcast, it's a beam. It's more like a laser than it is like an RF radio broadcast. And that changes the way you think about things. So that's kind of fun, right? It's fun and interesting and gives us some new ideas. So this is my one slide on motivation, which I absolutely don't need to show to this community because we all know that wireless and also wired systems, there's an increasing demand for data, and eventually we're going to need more than we can do, right? 5G is coming very soon, if not already here, and within a few years it will also already be saturated, and we will need more bandwidth than it can possibly provide, so we will need to move to higher frequencies. That's kind of, I don't really need to dwell on that, I think, for this group, right? This is one slide which I like to show. I think many of you might have already seen this, but I think it's important to emphasize. This is the channelization standard that has already been approved by the IEEE and will be under consideration at WRC 2019 next year in Geneva. And when I first saw this, I had several reactions, one of which was sort of the overwhelming joy of knowing that thinking about terahertz as a place to do wireless communications is not crazy because somebody else thinks about it, right, and has thought about it enough to put together a standards document, which is fantastic. So thank you to Thomas Kerner and Iwao Hosako for letting me use this slide. This is really very motivating, right, because it tells us that, somewhere between 252 gigahertz and 321 gigahertz, somebody might actually be doing communications someday. And if that someday is, not too far in the future, we better start thinking about it now. So I will dwell for just a minute on what do I mean by terahertz, right? And you can see I circled down here. Is this really terahertz? It's less than 300 gigahertz, which means the wavelength is more than a millimeter. And so is it really terahertz? Should we call it terahertz if it's below 300 gigahertz? I hate this question, right? Who cares? In my world, if it's above 100 gigahertz, it's terahertz. And, that's just lingo, right? Doesn't really matter. You can call it millimeter waves if you want to. But let me point out that the people who are strict about this and say you have to say millimeter waves if it's below 300 gigahertz, these are the same people who refer to those airport scanners made by L3 as millimeter wave scanners even though they're more than 10 millimeters. Ha! So there you go. Okay, so what's the plan for today? So a little bit of background on the terahertz field. This is sort of, I know many of you guys have heard a lot about terahertz already, but I'll spend a few minutes just kind of giving my perspective, and from what I call myself a teravangelist. I've been evangelizing the terahertz field for over 20 years now, and so I guess I've earned that title. And then I'll give a few examples from my research group over the past few years of work we've been doing on modulators for terahertz radiation, and these are external modulators, and I'll explain what I mean by that. The terahertz waveguides, which are a useful platform for doing all sorts of signal processing operations like filtering and switching and multiplexing, and I'll talk a little bit about how that works. And then, what is the channel like, right? If we really want to send terahertz signals from here to there through the air, what's different? What's the same at lower frequencies, and what's different? And how do we measure? How do we make those measurements? And then I'll finish up with our most recent work, which is an interesting question that we just started thinking about very recently, and that is if you have a terahertz wireless link, and it's just a point-to-point link, so not a network, but a single transmitter and a single receiver, and they're pointing at each other, are you still vulnerable to eavesdroppers? Right? And now if you do this with RF, you are, and people think a lot about this, and it's a big issue. At higher frequencies, presumably it gets harder, but the question is how much harder? And so we've begun to think about how to quantify that. So let me point out that the terahertz field is not brand new, right? This is the very first paper ever published in the journal Physical Review, right? The date on there is 1893. It's volume 1, issue 1, page 1. It's the very first paper ever published, and it was a terahertz spectroscopy paper. They did not use the word terahertz in those days. They called it obscure radiation, which it still is, right? But they had a source of terahertz radiation, they had a detector, they put things in between, and they measured absorption coefficients, right? And so people have been doing terahertz work for a long time, and in fact, in my lab today, we still make measurements basically just like that. We have a source, we have a detector, we measure absorption, okay? So, and there's still a lot of materials that haven't been characterized. I mean, a lot of stuff has been done, but there are many things that have not been done, and so there's still a lot of interest in basic spectroscopy in this range. So what has happened recently, of course, as I mentioned at the beginning, is that there is this sort of growing realization that the electronics people and the photonics people are talking about the same thing when they're talking about these, when they're both talking about 300 gigahertz, right? And so there's sort of a ongoing, I would say, merger of the electronics and photonics views of the world, which I think is great. It's what the field needs. And so, I'm very encouraged by this. It's been a long time coming. There's been, in recent years, a lot of progress in some key metrics, and this graph here shows one. This is power produced by various different sources, and by the way, I should point out the sources that are mentioned on this graph, that's by no means a complete list, right? That's just a representative list of some ways to generate power in this spectral range versus frequency, and you can see, this little blob down here is what you could get from silicon-based terahertz sources in 2008, and here we are in 2018. We've moved up by quite a few orders of magnitude. So, and that's silicon is one example. Other material systems have improved in similar ways, and that gives you a lot of hope that we really can eventually make integrated systems where you generate enough power to do something useful. But there are many important metrics, right? This is power. Power is not the only metric of relevance here, and this cartoon is supposed to be and I should credit Kaushik Sengupta from Princeton who made this graph and allowed me to use it. Thank you, Kaushik. This is supposed to illustrate, some of the different metrics that are relevant to terahertz devices and where we are and what we have to think about, right? It's not just power, it's efficiency, right? Or sensitivity of detection. It's not just generating a terahertz signal, but can you tune it? Can you electronically control the terahertz signal? Can you change the direction of the beam? Can you change the spectral content of the beam? Can you change the polarization? Can you do these things fast, right? Can you do it in a programmable, reconfigurable way? I think a lot of systems that we can envision in the future will need these sorts of capabilities that we, in many cases, don't yet have. So there's a lot of work still to do. These days, there are many options for terahertz sources. And again, this is only a representative cartoon picture of a few options, some of which may be familiar to you. There are certainly people in this room who know about these sources from Virginia diodes, these Schottky diodes and mixers. That's the sort of the electronics version. But there are, of course, terahertz lasers. Quantum cascade lasers are just simply diode lasers that operate at frequencies down below 2 terahertz these days. You may not know that one of the very first lasers ever built was a terahertz gas laser from the late 1960s. I don't know that you can buy one anymore, but up until a few years ago, you could. They're bulky and difficult to use and a pain in the neck, but they produce an awful lot of power. If you really want a watt, right,
What's
a watt, 1 watt, that's a lot of power, right? That's enough. When I say a lot of power, what I mean is if you put your hand in the beam, it hurts. Right? That's my metric for defining what a lot of power is. And so if you put your hand in front of a focused terahertz gas laser, it hurts. You don't do that, right? So on the other hand, it's 3 feet long and costs a lot of money and breaks off all the time. So you really don't, you're better off not using one, I would say. If you happen to have a spare $100 million, you can build a free electron laser and get a lot, hundreds of watts probably. But, well, enough said about that. My favorite source is this one. This is where my career began, or at least my career in terahertz, in the mid-1990s. The idea here is that you start with a femtosecond laser, which is producing a very short pulse of optical radiation in the near-infrared, and you down-convert it to terahertz using a nonlinear optical process. I'm not going to talk about the details too much. This is by now pretty well known. This was a technique that was developed in the late 1980s. By groups at Bell Labs and at IBM. And it is by now matured to a fairly sophisticated level where we can do an awful lot of measurements with these systems. And it's very powerful because it's very broadband, right? So it's continuous spectrum that spans the range from, well, the low frequency end is usually around 100 gigahertz or so, and that's limited by the size of the optics, actually. And the high frequency end can be several terahertz, 2, 3, 4 terahertz is very typical with these systems. So it's a nice tool for making sort of characterization measurements, characterizing devices and things like that. It's not really going to be easy to imagine putting it in a form factor that would fit in your pocket. That's less likely. But it's nevertheless a useful tool, which we make use of extensively in my lab. So this is the kind of thing that we measure. This picture in the upper right here shows the terahertz electric field versus time. That's a direct measurement straight out of the instrument without any post-processing at all. So it's a photocurrent versus the position of a mirror, which corresponds to a time delay, and that's terahertz electric field versus time. You can see it's a single cycle in the time domain, which means it's very broad in the frequency domain, and yeah, it's a powerful tool, I would say. It's also quite easy to build one of these if you want, or you can buy one. So nowadays, there's quite a few companies that are selling systems just like the one I showed you a schematic of. The whole system can be packaged in a box about the size of, well, this is about the size of a laptop computer or thereabouts, including the laser. It all fits in there, and you can make these terahertz time domain measurements. It's still not cheap. It's not the cost of a cell phone. It's more the cost of an extremely expensive automobile. Very expensive automobile. But, okay, nevertheless, it's a useful tool. And as I say, there's now a list of, I don't know, maybe there's 10 or 12 companies in the world that are selling these. Mostly for the research market, but there are also, these are some of the first terahertz systems that were sold for the commercial market, for actual applications outside of, university-based research. So terahertz imaging systems are used for quality control in factories. And these are the systems, this is the kind of system that's used for that purpose. So here's, so if you Google terahertz imaging, you'll come up with some sets of really interesting pictures, right? Some of these represent real-world applications that are in use today, right? This is from the news just a couple weeks ago. This company, TrueVision, is now going to be manufacturing these passive terahertz imaging systems. It's just a camera. It doesn't generate any terahertz radiation. It's just looking at thermal emission from people. And this will be for security screening. It's already used for security screening in European airports, and it will be used in US airports soon. And then these are some pictures that came from when I was a postdoc at Bell Labs, which I think are funny, but they're also interesting in what they illustrate, right? You really actually can count the almonds in a block of chocolate if you want to. Which may seem funny, but if you're the guy who manufactures the chocolate and is responsible for making sure there's enough almonds in every bar, well, maybe this is a good way to do it, right? On the other hand, there's a lot of hype, right? So be very careful. There's also a lot of stuff out there that is just absolute nonsense, right? You can very easily find images like this on the internet, which suggest that terahertz imaging could be used to see the bones in your hand through living tissue, which is complete nonsense. Don't get fooled by that, right? The absorption coefficient of water is very large. Water is opaque. You can't put terahertz through it unless it's extremely thin, right? Kind of 100 micron scale or less. So the penetration depth into you is very small. In fact, with our terahertz systems, it's easy to just stick your hand in the beam, and your hand acts as a reasonably good mirror for the terahertz beam. So you can build a system where the beam makes a 90-degree turn, pull out the mirror, and put in your hand. And you get something like a 50% reflection off your hand, something like that, with penetration of basically zero, less than the thickness of your skin in your palm. So there's a lot of hype, right? So be careful of that. But there's also a lot of real stuff, and that's the fun stuff, right? And so when you come to thinking about the real stuff, you have to say, well, what are the tools we need to make a system, right? And there are many, many challenges, right? And now I will focus mostly on communication systems, although imaging and sensing systems are also, of course, very interesting. In communication systems, there are many challenges. There are many challenges at many different layers, right? At all layers, right? And here I'm listing only a few, right? There's many bigger challenges even than the ones that I'm listing here. The ones I'm listing here happen to be the ones that are of interest to me personally. So that's a rather biased choice, but there's lots of challenges, right? What are the sources that we're going to use? How are we going to modulate the signals? How are we going to steer the beam, right? If the terahertz is a laser beam, if it's really directed and we want to do mobility, right? Someone walks across the room, the beam needs to follow them. And it needs to know where to go, and it needs to do that fast. Right? And that's a hard problem if you don't have a phased array. And we don't. There's no phased arrays at these frequencies that are at least not commercially available. I mean, if you have a lot of money in a big research lab, you can build one, maybe. But it's a challenge, right? So let me just give you an example, right? Optical modulators is a nice example, right? And here's where I want to define what I mean by an external device. I used that phrase earlier. Let me tell you what I mean, right? In optical systems, you can modulate an optical signal in two different ways. Number one, you can turn the source on and off, right? That's one way to do it. But number two is you can leave the source on all the time and then have a device in front of it that just blocks it and unblocks it, right? So that's an external device. And it turns out that in fiber optic systems, that's the way it's done. For a variety of reasons, that's better. And so the modulators are typically external modulators. And so here's a picture of something you can go out and buy. It's not even very expensive. This is a lithium niobate-based device. You drive it with an RF signal, and it modulates the optical transmission. And you can run these things at up to tens of gigabits per second, right? And that's a fairly cheap device, right? It's not expensive at all. It's fiber-coupled. It's easy to use. You can modulate both amplitude and phase, or both if you like. The insertion loss, right, when you put it in, how much loss do you get, is typically a few dB. 6 dB is sort of a worst case, I guess. The modulation depth, right, on-off ratio is 20 dB or better in these systems, right, and the speed is very high. Wouldn't it be nice if we had something like that for a terahertz beam? Something we could put in our terahertz beam and had all those same characteristics. We're nowhere near that, of course, right? So just to give you an idea, this was a paper from colleagues of mine at Los Alamos, which is now about 10 years old, where they demonstrated that you could use a metasurface, which is just a surface tiling on a 3.5 semiconductor, to do this modulation routine, right? You stick it in your terahertz beam, and when you put a voltage bias on it, you change the density of electrons in this doped layer, and therefore you change the terahertz transmission, right? And take the voltage off, the transmission recovers. And because of these little antenna patterns that are tiled in this array, it's a resonant effect because that's basically an antenna resonance. These things are about lambda over 10 in size, so they're subwavelength antennas, and you can tile the surface with them. That's called a metasurface, right? And so then you get a resonant transmission, which you can turn on and off, right? So to give you an idea of where the terahertz field was or is, right? This paper got a huge amount of attention. It was published in Nature. It's got 1,000 references or something like that. It was such a big deal because they had a modulation on-off ratio of 3 dB, right? Factor of 2 between on and off. And that was, right, that's terrible compared to optical modulators, but compared to anything that had been done in terahertz up to that point, it was better by factors of 1,000. Right? I mean, it was so much better. And it worked at room temperature, which most previous examples didn't. So it's a big step, but it also shows you how far we have still to go. So my group got interested in this technology and have done a number of kind of things with it. Okay, so this is from that same paper. Shows you you take your terahertz pulse. This is, again, one of those very short terahertz pulses. You shine it through the device, and you've got some voltage that you can put on there to turn it on and off. And you can see that the transmission swings on and off at this particular resonant frequency, in this case about 700 gigahertz, by 3 dB, right? That's the ratio between on and off. And if you try to turn the voltage up too much, of course, it saturates, and you don't get any additional change. And because we're measuring the electric field of the terahertz, you get not only the amplitude, but also the phase. So you see this very nice resonant response. And that's a nice modulator, although 3 dB, we'd really like to do better, right? So my group got interested in this, and we realized that there's sort of a good news, bad news story here for if you want to use this as a modulator, right? The good news is, by changing the size of those little antennas, I can tune that resonance to any frequency I want. So it's very tunable, right? If I want a modulator at 400 gigahertz, I can make one. If I want a modulator at 600, it's just scale the thing and make it a little bigger, that's all. It's reasonably fast. It's room temperature. It's got a fairly low insertion loss. It's controlled electrically, not optically. So it has a lot of the characteristics you would want. On the other hand, the modulation depth is not great, right? 3 dB. And the reason is because there's sort of a small interaction length. And so the question is there a way you can improve that? And we thought of a way to do this, which we've played with a little bit. And so one step is to, instead of tiling the entire surface with this metasurface array, you can break those pieces up into pixels and imagine having one little pad for each pixel. So now instead of one metasurface array, I have 16 of them, a 4x4 array, each one of which can be switched independently, right? So now each pixel can be turned on and off independently with a DC voltage. So that's now a spatial light modulator, right? Now the device that's projecting this on the screen, right? That's a spatial light modulator. That projector over there has a spatial light modulator in it, right? Which has 10 million pixels or something like that. Texas Instruments has been manufacturing these for years. It's a great technology. We got 16 pixels. So, we've got a little ways to go, but anyway, this was the first try. And it works, right? So here's a picture, an image of that device, a terahertz image, in which we're wiggling 2 of the pixels on and off and leaving the other ones grounded. And you can tell. So to make the device, I didn't mention how we made this. This is single-step photolithography on gallium arsenide. That's all it is. You put down a mask, you do photolithography, you do liftoff. That's it, right? And the wafer is just semi-insulating gallium arsenide wafer with a 1 micron thick doped epilayer on top. So that's a wafer that, if you have a friend with an MBE machine, he will make it for you, or maybe you can even buy it, right? So it's a fairly simple processing step. And the feature size, the smallest feature size here is, a couple microns. So it's sort of 1980s era lithography, right? We don't need a fancy stepper to make this work.
Is the thickness of gallium arsenide important?
Is it the fact that it's gallium arsenide important? No, not necessarily. Oh, the thickness of the gallium arsenide. The substrate is, it's just it's a semi-insulating substrate. It's just a transparent backing. So it's just for mechanical support. The 1 micron layer, yeah, that thickness does matter. If you make that, right, because what you're doing is you're creating a depletion zone by DC bias. And so if you make it too thick, then you're not going to deplete all the way through. And so then you'll still have a strong attenuation. And if you make it too thin, then you lose contrast. So there's an optimization there, and 1 micron's about right. Okay, so here's a device, a pixelated device, which shows this sort of modulation and every pixel's the same, of course. So, this is sort of the spectrum. Each one's about the same. And once again, about a factor of 2 on-off ratio, which is, for terahertz, not bad. We'd like to do better. But what we can do is modulate the terahertz wavefront, right? And so wavefront engineering is something that everyone knows is going to be important for wireless systems. This is, as far as I know, the first example of doing that other than mechanically. I mean, you can put your hand in the beam and block it, and I call that wavefront modulation, right? Sure. But, this is an electrical system where, and I love this example because in this case, you can see our 16 pixels, what we're doing here is grounding 2 columns, the ones shown in white, and the other 2 columns, we're flashing them on and off at a few kilohertz and just detecting the difference. And so if you think about what that is, it's a Young's double slit experiment. And we're just changing the widths of the slits at 3 kilohertz and detecting the difference. And so if you can calculate, and I gave this problem to a freshman in freshman physics who had just learned about diffraction and the Young's double slit experiment, right? The famous Young's double slit. I said, calculate the difference between this slit and this slit. And that's the red curves. And that was so exciting for the freshman that he decided to major in physics, which I consider a victory, right? That's, yay, we win. Okay, so anyway, you can modulate terahertz wavefronts, right? That's nice. That's a good thing to be able to do. But what we really want to do is improve our modulation depth. And so one way to do that is to make your pixels, instead of making them square, make them long and thin, right? So this is now the same sort of device, but the pixels are now columns. So each one of these, the gray is a column, and then the red is a column, and they're alternating, right? So if you think about what that is, right, that's a bunch of columns, each one with its own bias. If I bias them all the same, then this device is uniform across its face. And I'll get either transmission or not, depending on whether I've biased them all 0 or biased them all 10 volts, right? But if I bias them alternating, now it's a diffraction grating, and it will diffract light at some particular angle. So if I put my detector over there, I should see nothing if the device is biased all the same, and I should see something if the device is biased alternating. And so something divided by nothing is a big number, and there's your contrast. Instead of having 3 dB, right? You can do better. That's the idea. So this is just a zoom in on the device. The split ring resonator, the little antennas are they look a little different, but it's basically the same idea. They're just LC resonators in an array. The width of the column is about 1 wavelength. This device was designed to operate at, I think, 400 gigahertz, and so that's about 1 wavelength for 400 gigahertz. And it works. So you can shine your terahertz beam through it and look at the signal as a function of the angle of the receiver. And indeed, what you see is, if you look straight ahead, you see, this metamaterial resonance, which I've already showed you. You see this nice resonant behavior when the thing is biased. When we don't bias it, we don't have a depletion region, and the resonance goes away. Okay? So that's the resonance that's designed. But now if you look at a different angle, what you see is this big peak comes up if alternating columns are biased, which is not there if all the columns are biased, right? So in other words, you see a diffraction peak. And you can calculate the angle at which that should occur using, again, the freshman level diffraction theory, and it works perfectly. Okay? So it's just a diffraction grating. And so now what we can do is we can park our detector over here at the location of that diffracted light, and we can measure with the spectrum of what comes out, with alternating columns biased versus all columns biased, right? And this is the spectrum that what you see, and indeed what you observe is an on-off ratio greater than 20 dB. So that's a big improvement in the contrast for the modulator, right? But on the other hand, what I'm not telling you here is what's the efficiency? What fraction of the light is actually diffracted into this direction versus just go straight ahead? It turns out, again, you're working with a thin film, so the diffraction efficiency is still fairly low. So we still have some work to do to turn this into a really useful modulator, but it's got most of the characteristics, other than efficiency, most of the characteristics that you want for an external modulator. So it's still work in progress, but I think there's some promise there. So now let me switch gears a little bit, and instead of talking about these metasurfaces, which I think are very promising for a lot of different things, let me talk about waveguides. So in this room, people who are familiar with Virginia diodes think of waveguides as little holes in a piece of metal, right? Little circular pipes, right? Well, that's a very nice waveguide if you've got one frequency. But if your bandwidth is, like mine, 3 terahertz, that's not a very good waveguide because it has a cutoff, it's got dispersion, it's not a very useful device. So in my world, most people use something which is open on the sides. So you've got a pair of metal plates. So it's basically just, again, a metal waveguide with air, but in this case, instead of being closed on all 4 sides, it's open on 2 sides. And what that does is it removes the dispersion. So now the lowest order mode will propagate without dispersion at all, which means if I send in a single cycle pulse through one of these waveguides, what comes out looks exactly the same as what went in. It's reduced a little bit in amplitude from the loss, but the shape of the waveform has not changed at all. And that's the tool that most people actually use in the optics community. It's a nice tool for spectroscopy because your waveform isn't distorted by the waveguide itself. On the other hand, if I rotate the polarization by 90 degrees, now instead of exciting the TEM mode of the waveguide, I'm exciting a transverse electric mode, which is dispersive and has a cutoff. And you can see the difference in the waveform. It's spread out now. Instead of being a single cycle, I've taken all that energy and spread it out over hundreds of cycles, really, right? I'm only showing you the first 50 or so, but it rings for a long time, right? Because the speed of light now depends on frequency in this mode. And so, that spreads out things a lot, which you would think would be a tremendous disadvantage. But it turns out you can actually exploit that because that now means that the space between these 2 plates acts like an effective dielectric material. It's just air, but it acts like a material with a refractive index less than 1. In other words, with a phase velocity greater than c. And you can actually exploit that to make devices. So here's the basic idea. Rather than just one pair of plates, we're going to make a stack of plates so that we can do things in the 3rd dimension, right? And so here's a picture of a device that we made in my lab. This is a stack of metal plates with precise spacing, all the same, right? You're looking at it in the direction the beam would propagate. The beam would propagate into this picture. The width into the board is, a centimeter or less, maybe. And this stack of waveguides acts like a material with a refractive index less than 1, in other words, with a phase velocity greater than 1. And it's frequency dependent. And you can actually use this. Now, it turns out this idea is actually old. This idea was proposed even in the 1940s to make lenses. They called them lens antennas. I would just call it a dielectric lens, artificial dielectric lens. But you can see the size makes it a little bit impractical, right? So if you want to do this for 4 gigahertz, that's an actual normal-sized human being, right? That's not a little doll. That's like a real person, right? So you can see that's not a tremendously practical device, but now if you scale the frequency up, and the same idea, that's the device for 170 gigahertz, fits in your hand, right? It's this big. So now you have something that's really practical that you can actually use to make terahertz optics, right? Terahertz components that are passive, but give you capabilities that you don't have in any other way. Now, can we make terahertz lenses out of plastic? Sure we can, but plastic, even the best plastics, absorb a little bit, right? This thing absorbs nothing because it's air, right? I mean, you have to worry about the water vapor resonances, but other than that, it absorbs not at all. So it's a almost lossless lens, if you like. We can also configure it in a variety of other different ways. For example, if we take a stack of those waveguides, and now in this case, the stack is coming out of the screen at you, right? So there's a stack of plates coming out of the screen at you, and then here's another one, exactly the same, but at a different angle. And we illuminate it from the side with a terahertz beam. Now, just because of Snell's law, refraction causes the beam to change direction, and different frequencies will change by different angles because the phase velocity depends on frequency. And so now you have all of your frequencies in your beam spread out where you can access them individually, which means you've got a filter, right? An arbitrary filter. So I can just stick metal objects in there and filter out pieces of my beam. So I can make a high-pass filter or a low-pass filter with just metal and air. You can't get cheaper than that, right? It's passive, but it's incredibly robust, and it's completely reconfigurable. We can do high-pass, we can do low-pass, we can stick things in the middle of the beam, like this to make a band pass or a band stop filter, and this is arbitrarily tunable and scalable to essentially any frequency. And not only that, I mean, I don't know if it matters so much for, for this kind of applications, but it's also can handle arbitrarily high power. It's never going to damage because it's just metal and air, right? So it's really a nice idea for a reconfigurable filter, which I think could be really useful. And you can imagine packaging this in a way. I mean, we did it, of course, in some bulk way and using bulk optical components, so it doesn't look pretty. But you could easily imagine packaging this in a way that would really make it very robust. We've done other things with this same idea. So here's a demonstration of the same sort of waveguide stack as a polarization manipulation device. So this is a quarter wave plate. We can rotate. We can turn linear polarization to circular polarization. We can make an isolator by combining a quarter wave plate and a polarization filter. And so this is a terahertz isolator with isolation of about 50 dB in a narrow band. I mean, the bandwidth here is a few gigahertz, but it's 50 dB of isolation at any frequency you want. Just by changing the spacing between those plates, you tune the frequency. So I don't know, is a 50 dB isolator useful? Could be, right? And this is, it costs, nothing to manufacture, right? It's almost free because it's just thin steel plates screwed together. This is another interesting waveguide-based idea, which is a little bit more sophisticated, a little bit harder to make, but it gives you an interesting advantage, which is that it's an active device. You can electrically control it and change its properties. So this is, again, a filter. In this case, what we've done is we've taken 2 waveguides and coupled them together. So here's a waveguide on the top, and here's a waveguide on the bottom, and they're coupled together with a gap in between. And actually, that gap has in it a little glass capillary, which is filled with an electrically conductive liquid, and in this case, it's salt water or something equivalent, and then a liquid metal plug. So it's an indium gallium liquid plug, and it turns out if you put a voltage on the liquid, that plug will move back and forth with just a few volts. So you can actually use this as a channel add drop filter because the frequency that couples between the 2 waveguides depends on the size of that gap. And so you can design it to couple one particular frequency. So for example, here's one particular frequency is coupled out of the upper waveguide and into the bottom one. So it's an add-drop filter with a single channel. Now we can make multiple channels as well, and then you've got a multi-channel add-drop filter. Here's one with 3 channels, and this graph here is showing you the bit error rate of digital data sent through on the upper waveguide and measured on either the upper or the lower one, depending on the switching. So this is an electrically switchable channel add-drop for terahertz, operating at about 100. This one's operating at about 100 gigahertz, but again, it's scalable. You just scale the size by a factor of 2, and all of a sudden you're at 200 gigahertz. There's nothing in here that won't scale.
What is the spacing between the 2 waveguides?
In this example, the spacing between the 2 waveguides is I think a little bit over a millimeter. So it's, single mode waveguide. That's all it is. Millimeter and a half, maybe. I'm not sure. I don't remember exactly the number. So we can also use these parallel plate waveguides as a platform for multiplexing. So this is a leaky wave device. Here we have a pair of parallel metal plates. We cut a slot in one of them, and that lets some radiation leak out. And that turns out to be the basis for frequency multiplexing in the terahertz range. So let me show you how that works. So the device, here's a cartoon of what's going on. You shine light in over here, it comes out over here, and the angle at which it emerges is directly related to the frequency. So if you put in multiple frequencies, then each one will come out at its own angle, and you could imagine distributing different signals to different clients according to the frequency at which they're going to receive, right? So there's a one-to-one relation there. It's not linear, but it is at least one-to-one between frequency and angle, which is shown there. And so this is how you would use this device as a transmitter, right? And just reverse the arrows, and it's a receiver, right? So I figured I should show a picture of at least one experiment. This is sort of what it looks like in my lab. Here's our terahertz transmitter. You can't see the optical fiber coming in on the back here with the femtosecond laser, but it's there. These are plastic lenses which focus the terahertz onto this device, which I can zoom in on over here, and that's our leaky wave device in a receiver configuration. So we're shining light into the device, and the light will only couple into the device if it satisfies that angle-frequency relation. So you can measure this in a receiver configuration like I just showed you, and in fact, of course, it works beautifully, right? And notice the range of frequencies over which we're working here from about 50 gigahertz up to about 500. This is using the device in the other configuration where you've got light propagating in the waveguide and looking at what comes out, which again is the exact same frequency-angle relationship. And so now we can imagine putting in 2 different frequencies, each of which has its own independent data, on a terahertz carrier, 2 different terahertz carriers with 2 different frequencies, and each of them will come out at a different angle, and therefore they will be demultiplexed, right, and broadcast to some user 10 meters away or whatever who's expecting a particular frequency, and that determines the data he gets. So that works, turns out. So here's coupling 2 different frequencies in. This is the opposite idea, where you put 2 frequencies in from 2 different angles. And you see that indeed, if you shine light on this thing from 2 different angles, you get 2 different frequencies. And of course, one of them tunes. As you tune the angle, you tune the frequency. Again, just as you would expect. And this works with data. So we then took 2 different data streams at 2 different frequencies, put them into one of these devices, let it propagate in the waveguide for a few centimeters, and then another slot where it can couple out. And we actually can get pretty good eye diagrams and bit error rates of about 10 to the minus 5 or 10 to the minus 6 on those 2 channels independently. And of course, there's no crosstalk because the frequencies are different, right? And this is a passive device. There's no way for 2 frequencies to couple to each other. So it's a very robust multiplexer. And we did up to 50 gigabits per second through this mux-demux device. There's an interesting effect of detector aperture here, which I think is actually very general. It's not, I think any multi-frequency terahertz communication system is going to suffer from this problem. Well, I don't know if I should call it a problem. It is going to experience this issue. And that is that if you have a very broad band of frequencies, and you've got anything in your system that has diffraction or refraction, there'll be a frequency dependence to the angle. That's inevitable. In this device, it's built in, but in any device, it's pretty much inevitable. And that means that your detector is going to see different frequencies across its face. And that changes your bit error rate. That actually impacts your bit error rate. And if you have a MIMO system, it's going to be even worse, right? So this is something that you really have to think about. This is some experimental measurements and a simulation to show that. And what the effect that has in our system is, as we raise the data rate from 1 gigabit per second to 6 gigabits per second, the angle over which we can receive the signal decreases because of this effect. So that's a disadvantage, but maybe it's also an advantage. If you have a MIMO system, you could actually use this to improve your data rates with clever signal processing, which is something I know nothing about, but I'm sure it will work because those guys are smart, right? Okay, so let me move on to other measurements that we've made in my lab recently. Since I moved to Brown a few years ago, we bought this system here, which is familiar to many of you. This is just Virginia diodes, tools, and we can broadcast signals at 100 gigahertz, 200, 300, and 400 with reasonable power. I mean, compared to the femtosecond laser-based systems, way more power, way more power. But not tunable, right? Single frequency, and we can modulate at a gigabit per second, so we can actually do tests of sort of simulated real channels, right? Real wireless channels. And we have a license from the FCC to do outdoor tests up to 400 gigahertz. So we can actually do this legally, which is kind of nice. Let me show you this picture here. This is a little bit, oh, that's a little distorted. That picture's a little weird. Okay, so this is an interesting, this summary, and I have to apologize, it's a bit out of date. But this shows a bunch of different publications. We tried to capture them all, which have done different data rates and different frequencies. And here's distance and frequency. And this one's distorted in a way which I apologize, you can't really see. That's strange. I wonder why that happened. But no, the bottom line here is that people are doing measurements all the way up to 700 gigahertz at ranges from centimeter to kilometer. Well, of course, the higher frequency you go, the shorter the range is. But you can see even at the low frequency ends, even up to a couple hundred gigahertz, people are doing kind of hundreds of meters or kilometer scale tests outdoors. We're doing indoor tests and outdoor tests. And I want to point out on this graph over here, which comes from this paper, so it's a couple of years old by now, but all of the data points on here are labeled according to the country in which the experiment was done, and you will notice that very few of them say US next to them. I'm hoping that situation will change because we need to catch up. So we're trying to catch up in my lab by doing some measurements, and here's one example where we just took our VDI system and took it out into the hallway outside the lab where there's a cinder block wall and just pointed it at the wall and bounced it off the wall, and it works. The wall is acting like a mirror, so it's not scattering very much. It's a specular reflection off the wall. And these are data curves at 100 gigahertz, 200, 300, and 400. And you can see that in all four cases, we can achieve a bit error rate of 10 to the minus 9, which is pretty good, right? We can distinguish where the loss is coming from by putting a conformal aluminum foil plate, or just aluminum foil pressed onto the wall, so that preserves the surface roughness, but eliminates the penetration of the signal into the cinder block. And so therefore we can distinguish between scattering losses and absorption losses. And what we find is that in this particular case, the absorption accounts for like 10 out of the, say, 14 dB of total loss, something like that. So the absorption is really the biggest effect. The fact that the surface is rough doesn't make that much of a difference. It's a few dB, which surprised me. I thought it would be the other way around. So it's nice, it's nice to learn things, right? So this really works. I mean, you really can bounce the signal off a wall, and in fact, you can do it twice if you want to. This shows you the signal being bounced off of the wall and then bounced off of the wall again. This transmitter and receiver, there's no direct line of sight between them. They cannot see each other. They're around a corner. But you can go bounce off the wall twice, and these are specular reflections, right? Angle of incidence equals angle of reflection. The wall is acting like a mirror. And with, there's a loss. There certainly is some loss, but even at 200 gigahertz, we can, with a very modest output power from the transmitter, we can get a bit error rate of 10 to the minus 9 going around a corner. So this really suggests that these links are pretty reasonably robust, that it's actually got a good chance of actually working. We've also done some outdoor tests. This is outdoors above, just a sidewalk, and this is outdoors above a grass field. This is on campus at Brown University. And actually, you see a difference between propagating over a sidewalk versus propagating over grass, because if you're propagating over grass, then the specular reflection off the ground is eliminated because the grass is wet. And so you don't see interference from that. And so your signals are actually a little better over the grass for that reason. Not very big difference because it wasn't a very wet day. But you can imagine if we did it the day after a rainstorm, it would be different, right? We've also measured snow. This is something that I could not do when I was a professor in Houston because it never snows. But moving to Brown has its advantages, right? We knew there was a snowstorm coming. We looked at the weather. We said, there's snow coming tonight. And I said to my postdoc, go put the stuff outside and stand out there all night and measure. Well, not all. He wasn't out there all night, but he's a hero. He's an absolute hero because he did these measurements. It was cold. And someone, he had to stand there with an umbrella over the equipment to keep it dry, right, and everything. Oh, what a nightmare. Anyway, he did it, and what we found is that at least for this particular snowstorm, snow is bad because the snowflakes scatter a lot. They absorb, but they also scatter a lot because they're about a wavelength across. And so the scattering loss and the absorption loss are very comparable for this particular snowstorm on this particular day. I don't know if I could generalize that, but 3 dB loss in 10 meters or something, which is a lot, right? So snow is tough. Worse than rain, I think. So now let me finish up by asking this question, right? And I think we all know that wireless security is a big deal, right? When you're broadcasting in a 120-degree sector and your intended receiver's over there, then an eavesdropper can sit over there and hear what you're saying, right? So how do you fix that problem? Well, of course, there's a lot of ways to fix that problem. You can do wavefront engineering, you can encode, you encrypt your data. I mean, there's a lot of things, right? Everyone has said for a long time that if you go to higher frequencies and your beam gets narrower, then your security should improve, right? Because the eavesdropper can't sit over there anymore, right? The eavesdropper has to sit sort of in between you and the transmitter, which means that the eavesdropper will block the transmission, which means that the eavesdropper will be noticed, right? And that if the beam is narrow enough, that should mean that the eavesdropping is impossible, right? That's kind of been the conventional wisdom, which people have said for many years, right? So if the beam is directional enough, this conventional attack will fail, right, due to blockage. The eavesdropper cannot avoid blocking the intended receiver and thereby raising an alarm, right? So we decided to test this, right? And the bottom line here is that you would never design a system where the beam size is exactly equal to the aperture of the receiver, because then you have no margin for error in aiming. So it's got to be bigger. And if it's bigger, that means that an eavesdropper can somehow get in there, right? And so we did this test at 3 different frequencies, 100 gigahertz, 200, and 400, and you can see our beam angular width gets quite small, right? At the highest frequencies, it's less than 2 degrees angular width. This data shows the 200 gigahertz, but all 3 of these are very narrow. So, if under ordinary circumstances, Eve would sit in there, and her shadow would fall on Bob, and then Bob would know she was there. And so the eavesdropping attack would fail. The question we wanted to know is, can you do that? Can you, instead of putting your receiver in the beam, can you put a little piece of metal in the beam, something small, that casts a tiny shadow so that Bob doesn't get shadowed, and therefore Bob doesn't get blocked, but still large enough that it scatters enough signal towards Eve so that she can actually decode the signal, right? Is there a sweet spot where the object is small enough to not cast a shadow, but big enough to scatter enough radiation so that the eavesdropper can see it? And when we started out these measurements, the answer was not clear that there would be such a sweet spot, right? But it turns out there is, at all frequencies. You can make this work at all frequencies if you're smart. So here's our test bed, right? It's a transmitter and a receiver and a piece of metal in between. I mean, that's what we call a test bed at Brown University, right? The hardest part of these experiments was finding a room big enough to do these experiments, which no one was using for something else. And we had to wait till Christmas break to do it, which worked. And so this shows you some sample data of scattering signal, and this shows you the ratio of the scattered signal received by Eve divided by the power broadcast by Alice as a function of the position of the receiver, in other words, the angular position. And you can see these are for cylindrical objects. So cylindrical objects will scatter in all directions. So you can see there's scattered signal at all angles. All right? The dashed lines are predictions from a numerical, ab initio numerical calculation that assumes nothing at all, just the power and the size of the object. So the physics is right. So this is the interesting result, right? So this shows you how much of the beam is blocked, that's the solid curves, and how secret is it? In other words, what is Eve's signal to noise compared to Bob's, right? If Eve is getting the same signal to noise as Bob, then the secrecy capacity is 0, meaning Eve decodes the signal 100% of the time, right? So you can see that the secrecy capacity does indeed go to 0 for larger objects, but of course the blockage is large too. And so that would be a fail for Eve, right? Eve has failed. But that's if you put the pipe right in the middle of the beam, where it's guaranteed to cast a shadow on Bob. If you move it over, just by one pipe diameter, now Eve wins, right? You just move it over by one pipe diameter, and so all of a sudden Eve wins, right? The blockage is still not 0, but it's much smaller, and the secrecy capacity is quite small. So Eve can actually win. And this is with a cylindrical object, which means Eve can put herself at any angle she wants and get the equal amount of signal, almost. If she uses flat plates, it's even worse, Because now Eve, the signal's all going in one direction. Now it's just a mirror, basically, right? A flat metal plate is a mirror. And so now all the signals, so Eve has lost her freedom to be at any angle, but her signal to noise is much higher, and the blockage is basically zero, right, if the plate is off axis. So if you put a flat metal plate in here, you're not shadowing Bob at all, so the blockage is basically zero, and the secrecy capacity is also very low. So Eve basically has less freedom, but more success. And this works at every frequency, right? Every frequency we tested. So it doesn't mean that terahertz links are not secure. They are more secure than links at lower frequencies. That is still true. But you can't say they are 100% secure because the beam is narrow, which people in the past have said. And that's kind of the lesson here, is that you still have to think about wireless security. It gets even worse. If Eve is clever and has the freedom to engineer a beam splitter that splits off a desired fraction of the beam, and she can choose that fraction, then she wins 100% of the time, it turns out. There's a sweet spot here where if she chooses just the right transmission coefficient for her beam splitter, the blockage is too low, the backscatter is too low, there's no win. Eve wins every time. The bad guy always wins. So if the bad guy is sufficiently smart and agile and clever, then they will win, no matter what you do. So, unless you have other mechanisms in place, obviously, you're going to encrypt your data, right? I didn't mention anything about that, right? So this is just considering whether or not, as the beam gets narrower, does it really get impossible for an eavesdropper to grab a piece of it? And the answer is no. Even if the beam is very narrow, it's still possible. Even for optical communications, even if you communicate with lasers, free space lasers, this was still true, right? You can always still catch some of the scattered light, right? So this is sort of a vulnerability which exists no matter what frequency you're at, that people maybe previously haven't considered so much. Okay, so let me wrap up. So my conclusions are sort of, I guess, pretty obvious, right? Number one, I believe that terahertz communications will be inevitable. We will be using these frequencies above 100 gigahertz for wireless data links in the future, so we better get working on it now. There are many challenges. I've only listed a few of them, right? There are many, many, many challenges that I have not discussed, so this is a big problem. You've heard about some of them from some of the other speakers in this series, and so I'm hoping that my talk is sort of a little complementary to theirs in the sense that I'm focusing on other aspects of the challenge than what you've previously heard about. I think these external devices are maybe not the only answer, but they're a promising platform for doing cool things with signal processing, which may be better with respect to, say, energy efficiency or speed or price or whatever. The channel characteristics, I think there's still a lot that we don't know. There's a lot of conventional wisdom that needs to be overturned. There are still many people in the world who believe that you can't bounce the terahertz beam off the wall. And you really can. No matter what your frequency is, you really can. Sort of my final answer here is that when you come to talking about links above 100 gigahertz, this is not merely microwaves with a few extra zeros, right? It's more subtle than that. The differences there are significant, both in the physics and in the devices and in the implementation. It's different in many ways. And that makes it interesting and fun, of course. So thank you for your attention.
Thank you very much, Professor Mittleman, for that terrific talk, taking us from optics to these devices you've made, waveguides, multiplexers, bouncing off walls at terahertz frequencies. It's terrific. I'm sure we have some questions. Questions for Professor Mittleman? Yes.
Is it possible from a hardware standpoint to improve the security of the link?
The question is, would it be possible to improve the link security from a hardware standpoint? And I assume you mean from a physical layer standpoint. So there's a variety of ideas that people are exploring. Certainly, at lower frequencies, people talk about wavefront engineering, right? This idea of you broadcast a wavefront that goes in many directions, but the data is only decodable in one direction, and in other directions it's noise. That in principle ought to work at terahertz too, although it's a more subtle problem because in this case, your beam is very narrow. So, the change has to be much more rapid as a function of transverse position, which might get really hard. So I don't know how effective that's going to be. That, I think, is still an open question.
Other questions? So I've got one for you, Dan. Great talk.
Thanks.
Really exciting. We're doing some of these same kinds of measurements, but we're not at 300 and 400 gigahertz yet. We're at 140 gigahertz.
Yep.
And we've got the wireless class actually looking at the scattering models. And we found the same thing, that the rough scattering reflection coefficient model shows you'll get a lot of energy bouncing off in the reflective direction from rough surfaces. What have you found to be, in the literature, the best scattering models for up in these terahertz range? Because the mobile industry never's really considered scattering before, because
Right.
it's really such a low-level effect down at mobile frequencies. But as we go to millimeter wave and terahertz, we need to know what scattering is. What have you found in the literature?
So the subject of scattering off of rough surfaces is a big deal in optics, as you can imagine.
Sure.
People have developed extremely, I mean, there are full textbooks on this subject.
There's
And
not a lot of work at how it works at terahertz and sub-terahertz. What have you seen?
that's right. So there's been a little bit of work. We published a little bit on that about 10 years ago, one model, which is basically a simple, estimate your surface roughness with a single parameter that's sort of the RMS height variation, and then just sort of exponentially attenuate your beam according to that, right? And that works okay if your roughness isn't too much.
The direct scattering
Yeah,
model?
yeah. But then if the surface gets rougher, and actually we're doing some measurements on this right now, if the surface gets rougher, we've engineered some artificially rather rough surfaces and made them out of metal so that we don't have to worry about attenuation due to penetration. Then you see multiple scattering phenomena on the surface. So your beam will actually, the photons, if I can use that word, right, will actually scatter more than once on the surface before they leave. And that leads to interesting correlations. And you can use that because actually what we've done now is we've shown that even in the non-specular directions, a few degrees off, you can still get data transmission, which is nice. But you need the surface to be pretty rough. So, and there are models for this. Like I say, there are textbooks on this people have done, and what we're trying to do is adapt models that have been developed for optics and use them at terahertz. I think it's an important problem because, among other things, what we see on these rough surfaces is polarization rotation. So the beam comes in polarized this way, some fraction of it comes out this way, and if you're trying to do polarization multiplexing, that's going to really, really ruin your life, right? So one needs to characterize this because these sorts of rough surfaces, I mean, it's not so rough. It's rougher than a typical indoor wall, but it's not for outdoor. It's the kind of roughness you're going to see all the time.
That's right. Yeah.
So,
other questions? Well, your students are out in snow. You're up at 500 gigahertz. You're down at 50 gigahertz. You're sending 50 gigabit per second. Let's give Professor Mittleman a huge thank you for this great lecture in the seminar series. Thank you, Dan.
thanks for the invitation. I really appreciate it.
And we have a presentation for